some of the properties of lightweight aggregate, and then I'll go on with lightweight concrete. So it's quite general. And then finally, I'll share with you some of the work that I'm currently working on in our structures lab here at Northumbria University. So I will start first with structures made from lightweight aggregate. So they are not new. The Romans built the Pantheon 2000 years ago, and until today, it's still the largest unreinforced concrete dome in the world, and it measures about 43 meters in diameter. And its dome is made of lightweight aggregate. And so this happened in 126 to 128 AD. So that's 2000 years ago. They were already using lightweight aggregate. So how they built and how they envisioned the construction was the dome itself, it got thinner as it moved up from the base to the top. So the base here is 6.4 meter in thickness, and towards the top it's 1.2 meter in thickness. So at the base the material was made with travertine, and at the top it's made from turf and scoria. So there was an analysis done, and if this same dome was made using normal weight concrete, it would probably weigh 80% more in terms of weight, and it will require reinforcement. So like I said, the Romans built this without any reinforcement, and it's still the largest unreinforced concrete dome in the world. And the next significant structure, and I think this would be real impact throughout the world. This was 100 years ago, and it's the first commercial plant dedicated specifically to manufacturing of expanded shale aggregate. Um, so this was in Kansas City, Missouri in 1920. So the Southwestern Bell Telephone Company office, uh, it was originally built 14-story, and the company decided that it needs an expansion. So the expansion they were anticipating was 8 floors above the existing 14 stories. However, when they finally decided to go ahead with construction, they calculated and they thought, okay, they can proceed with the construction using lightweight aggregates and can actually double the height of this building. So instead of the existing 14 stories, they actually built an extra 14 floors on top of the 14 stories, making it 28 story high. So this building is still uh, it's still standing in Kansas, Missouri. So using lightweight aggregate, they managed to save about 4 million kilogram of dead load of the structure. Now I'll briefly go through what is lightweight aggregate and the properties of lightweight aggregate. So the properties vary depending on source and processing, and I'll go through some of the basic properties that we look at when it's lightweight aggregate. So this type of aggregate can be crushed or uncrushed. So we see them in a very varied range of particle size. So they can be replaced with normal weight aggregate in terms of coarse aggregate, which is more than 5 millimeters, or lesser than 5 millimeters as fine aggregate. So the general classification for lightweight aggregate is one, in terms of natural aggregate. We can find lightweight aggregate in its natural form. So this is mainly from volcanic ash and volcanic gas. So aggregates like pumice and scoria, they are natural aggregates. And I think a lot of the volcanic regions will have this form of aggregates. And then we also have artificial forms of aggregates. So these are mostly aggregates that has been taken and then heated up to probably around 2000 degree Fahrenheit and then crushed, and we use them as artificial aggregates. And today there is so many types of industrial waste lightweight aggregates. So this can come in terms of cenosphere, sintered fly ash. So both cenosphere and sintered fly ash is from the coal industry. So cenosphere is slightly larger it's void in the center. So both is from the coal industry. Then we have ceramicite, slag, and etc. So all these are the basic classification for lightweight aggregate. Now, but what we have today is mostly we don't really use natural forms of lightweight aggregate. Most of this come from manufactured product. So if you look at this diagram here, on my left, it's the basic getting your aggregates, digging it out from the ground, you possibly from volcanic regions or from just your normal quarry. So the raw material is usually clay, slate, or shale. So these are the three main types of aggregates that they use to produce lightweight aggregate. And and then the process then involve a production in the rotary kiln. So the rotary kiln will at on the right top here. So it's very similar to cement production. So it will go through various routes, and the main activity here would be the heating of this aggregate. So if you can imagine, the aggregates actually go on top of the fire, which is about 2000 degree Fahrenheit, and it sort of creates this gas bubbles, and that gas bubble will actually form these vestibules on the aggregate itself. So the aggregates are not melted, they are just softened. They form this sort of expansion on the aggregates, and then once it's formed, it will be crushed, and then it's screened and then ready for selling out in the manufacturing plants. Now, the first type here I want to share with you is pumice. So pumice is a type of natural aggregate, and it's used a lot in cosmetics. So for example, we use it in, cleaning out our dead skin and things like that. So that's pumice stone. Pumice is created from super high heat. It's highly pressurized rock, and it's rapidly ejected from a volcano. It usually comes from volcano regions. So if you look at the diagram of a volcano that I have, you can see two types of area. One is very dark, and one is probably where the lava has gone through. It's lighter. The aggregates are white, mostly whitish with some with a lots of holes, or what we call the vestibules. The bulk density of this type of aggregate is around 300 to 500 kilogram per meter cube. Now, to compare that with normal weight aggregate is around 1,005, 2,000 kilogram per meter cube. So this is almost 1/3 the weight of normal weight aggregate. And pumice, the specific gravity is less than 1, so it means that this type of aggregate will actually float on water. So often in volcanic regions, you can see this type of aggregates floating in water. Now, scoria is another type of volcanic aggregate. It's very large. It has these large vesicles, as you can see in this diagram. The walls are thicker than pumice, and of course, as you can see in the image, it's not as white as pumice, but it's very dark. It's dark colored. It's also from a volcanic lava flow, and it's an abundance of trapped gas. So all these voids that you actually see on scoria are trapped gas. And so it looks like a molten blob because it comes from the volcanic lava. So, and it's cooled in air. The specific gravity is more than 1. So this, if it's more than 1, then definitely this type of aggregate will sink in water. It's denser than pumice. Like I said, the walls are thick, so it's much thicker than pumice. Pumice has a very light kind of skin on it. The bulk density is higher than pumice, so it is 700 to 900 kilogram per meter cube. This type of aggregate is called vermiculite. It's mica-like. It's phyllosilicate. So it's a type of silicate mineral, and it's treated with extreme heat and pressure to force it to expand. So during this process, what actually happens to vermiculite is it expands and it forms like a worm. So it's curly in appearance, and you can see in that diagram. So I suppose you would know this word better than myself. Vermiculus means insect or larva. So I suppose from the way this type of aggregates look, it looks like an insect or a larva. So the term vermiculite was used. It's used a lot in horticulture. So vermiculite you can find very often in gardening shops, and you can use it for gardening as well because it can absorb water. It retains water in its particle, so it's very good for gardening purpose as well. Now the bulk density of vermiculite is between 700 to 1,000 kilogram per meter cube, and the specific gravity is much higher than the two aggregates that we just saw. So this is between it's above 2.2 or 2.3. Perlite is another type of volcanic aggregate as well, and this is commonly known as the volcanic popcorn for very obvious reasons. If you looked at this diagram without me telling you it's an aggregate, it will look like a popcorn. It's made by heating volcanic glass to super high temperatures. So different forms of heating on different materials from the volcanic area produces this type of lightweight aggregate. And you can see that the production of lightweight aggregate today actually mimics all these processes that we have been looking at. It's that high heat on aggregates that's causing it to have that porous microstructure and has that lightweight properties. So it expands and it pops. So this white porous lightweight aggregate also looks like styrofoam balls. So very often you find that concrete manufacturers, and we are working with one at the moment, who wants a kind of white looking concrete, they often use perlite in their mixed design. So this is one of the lightest form of lightweight aggregate. It's between 100 to 400 kilogram per meter cube. The specific gravity is about 2.2, 2.3. There's also other forms of lightweight aggregates that we have today and we use, and especially in research, they are very common. Um, for example, expanded clay. The one in A here is expanded clay. Xenosphere, like I mentioned, is a byproduct of the coal industry. Sintered fly ash is also a byproduct from coal industry. So xenosphere is much larger actually than the sintered fly ash. Then we have palm oil clinkers. So palm oil clinkers, suppose it won't be very common here in the European region, but it is common in Asia where you have the palm oil industry. It's a byproduct from the palm oil industry. Then we also have slate and shale ceramics. So these are all different types of lightweight aggregates that we use in lightweight concrete. So when we actually research how many percentage of aggregates are used for this various application, we find that expanded clay came out as the highest percentage that is used for lightweight concrete purposes, then followed by xenosphere, sintered fly ash, and so on. Now I'll move into one of the uh, main ideas around lightweight concrete, which is associated to its properties. Now, water absorption is one of the key properties that we look at when we are researching lightweight aggregate, and this is for obvious reason. So, because water absorption of lightweight aggregate is significantly higher than normal weight aggregate, because of this high porosity, it traps more water particles in its structure. This may range from 5% to more than 30% by mass of dry aggregate after soaking for 24 hours. So it depends on the source and size. We cannot specifically say that this aggregate will have this much of water absorption properties. It will not, because it really depends on where we are getting the aggregates from, what are the size, and etc. So water absorption definitely affects the workability of concrete, because now we have to consider the amount of water that is actually being trapped inside the aggregates. Um, Lightweight aggregate actually reduces the effective water binder ratio. So like I said, this has to be seriously considered when we are using lightweight aggregate. Consequently, it will reduce the overall strength, because now we have higher water binder ratio. It will reduce the overall strength. So due to this reason, often on construction sites where they are using lightweight aggregate, they are using it in the form of pre-wetting the lightweight aggregate, so that then we can adjust the amount of water binder ratio later on. Absorption alone, having said that, water absorption is a key criteria for lightweight aggregate, water absorption alone should not be considered as acceptable performance of lightweight aggregate, because they have other interesting characteristics to be incorporated in concrete. Only a fraction of pore volume fills water. So this is 20 to 50% of the pores are actually filled with water. So, and another thing I would like to really highlight is that the pores are actually not interconnected. So, it's only mainly the surface, and it does not act like sponge. So here I have the water absorption properties of different type of aggregates that were found. And you can see that at 24 hours, which is the general standard for water absorption tests, that the range is really high. It can be from, like I said, 30% of water absorption capacity. However, when we normalize the value at 24 hours, we find that all the aggregates reach at that point 1. This is because the water absorption peaks at 24 hours, and after that 24 hours, it kind of stabilizes, and we find that after normalization of the values at 24 hours, it all kind of stabilizes throughout up to 48 hours. So it's within that 24 hours that the water absorption characteristics is really high. Now, another characteristics or the property of lightweight aggregate that is key is the density of all this type of aggregates. And this is one of the main things that we look at when we are designing lightweight concrete with lightweight aggregates. So the particle density, so two main forms of density: the particle density, which relates to the mass of solids per unit volume of this individual aggregate particles, and also the bulk density. Now, very often we define lightweight aggregates with its bulk density rather than the particle density. This is mainly because we are including the volume of voids in the material itself. So the bulk density ranges, it has very high range. So for expanded clay, cenosphere, sintered fly ash, shale ceramics, so all the bulk density varies. And like I said, it depends on the size, it depends on the source of the materials. Similarly, with specific gravity as well, usually for most type of lightweight aggregates, it's between 1.3 to 1.6. No, if I compare that to normal weight aggregate, that's around 2.6 to 3. So that's half the mass for the same volume of aggregate. Now, when we check for lightweight aggregate in terms of its durability, it passes all the abrasion, LA abrasion tests, free thought tests for aggregates, and soundness tests. So there isn't really a concern in terms of the durability of lightweight aggregates itself. Um, then we have the aggregate crushing strength. Often the aggregate crushing value or the aggregate impact value is what is presented. So these values differ with different aggregates, like I've shown here. And one of the key things I would like to highlight, if you are thinking of using lightweight aggregate, I often find that the modified Anderson and Anderson method is very well. It proportions the aggregates very well, and we get a very nice mix when using this modified Anderson and Anderson method for the mixed design of lightweight concrete. So the final aggregate size increases the strength of lightweight concrete, and it's vital to have reliable particle size distribution. So the packing of the aggregates is really key here. It's really essential to ensure that it's packed properly so that we get a mix that is achieves all the strength requirements that we would like to have. Internal curing is, like I mentioned previously, is this is very important with lightweight aggregate because the water absorbed in the lightweight aggregate, it does not affect the mixed water or water cement ratio, and it's released over time in concrete. So if we have internal curing, so we are expecting it to increase in time, and the pre-wetted lightweight aggregate delivers internal curing and improves cement hydration. So often when it's internally cured, we find that the compressive strength is improved, the permeability properties is increased, and it also reduces shrinkage and cracking. Now here I want to quickly share with you an image of two types of slabs. One is with internal curing and the other without internal curing. So it's very obvious that the one with internal curing is nice, and it's still it's still curing in bit time, whereas the one without internal curing, the water has completely hydrated, and it's gone dry. And that's one of the things that I observe when making lightweight concrete with lightweight aggregates. The water content has to be adjusted accordingly. Now I'll quickly move on to properties of lightweight concrete. Um, so lightweight concrete, in terms of its definition, it there's various standards, and the standards basically say that the oven dry density is less than 2000 kilogram per meter cube. So we have seen in research it goes from 800 to about 2000 kilogram per meter cube. And like I said previously, lightweight concrete, it's not new. ASHTO, the American Standard for Highway and Transport, has lightweight concrete in its structural application since 1969. The Federal Highway Administration for the USA also have it for building bridges from 1985. And in general, low density concrete, which is between 300 to 800, has very low compressive strength, and this increases for structural application. Usually, density of lightweight concrete with 1350 to 1920 has about a compressive strength of 17 to 63 MPa. And here, most of the BS standards for lightweight concrete is only for below 40 MPa. Now, types of lightweight concrete, we have lightweight aggregate concrete, aerated concrete, and no fines concrete. So my presentation today is mainly on lightweight aggregate concrete. So I'm not going to look at aerated or no fines concrete. So some tests show that lightweight concrete has reduced compressive strength when compared to normal weight concrete. So even when lightweight concrete properties may be reduced, designs have been successfully completed and structures have performed well. And and when we observe a reduced tensile strength, some designers have specified higher compressive strength or add fibers or tensile mesh and so on. The modulus of elasticity for lightweight concrete is definitely marginally lower than the normal weight concrete. Mixing, batching, and placing procedures is generally about the same. Some designers prefer pre-wetted aggregate to allow for water cement considerations. Now, from research, we find that there's better bonding of lightweight aggregate and cement base. Therefore, it shows a good homogeneous property and less possibility of cracking and of concrete due to shrinkage, creep, thermal deformation, and so on. And lightweight concrete has also higher fire resistance. And different studies have shown sometimes lesser chloride penetration, sometimes more chloride penetration. And I'll show you later on some of my papers, which you can refer to look at those properties. Now, structural application of lightweight concrete has many different applications. So, for precast concrete structures, for construction of offshore platforms, insulation purposes for walls, and so on. Now, I'll share with you some of the key benefits of using lightweight aggregate in lightweight concrete. So reduce weight, so which is very obvious, it's the reduce weight. So it makes this easier to handle, transport and install. It reduces the overall structural load of a building. So you can extend the span, you can and reduce the design load. It has environmental benefits and cost saving. It uses less natural resources, obviously, such as sand and gravel, because now you can have a lighter structure. It can reduce the carbon footprint of a building due to its lower weight, and which requires less energy for transportation and also lower foundation costs. And one of the key benefits of using lightweight aggregate is the improved thermal and sound insulation. Lightweight concrete often have thermal and sound insulation because of this pore structures, the porous nature of lightweight aggregate. It can regulate temperature and reduce heating and cooling costs. Enhance fire resistance. So my research have done a lot of work on the fire resistance of lightweight concrete, and you can see a marginally about 20% of improvement in terms of fire performance of lightweight aggregate concrete. And it also, in terms of alkali aggregate reaction, because of that lower calcium, lower silicate content, your AAR values are much lower. The alkali aggregate reaction is much lower for aggregates, lightweight aggregates in concrete. Now, the current trend, we are moving on with the current trend of lightweight concrete. Lightweight high strength. Now, very often we find researchers working towards lightweight, high strength concrete. So high strength here is above 40 MPa, and so it fulfills both the criteria. So it fulfills that above 40 MPa, and it also fulfills the density of below 2000 kilogram per meter cube. Um, so here we can see that for high lightweight, high strength concretes, usually the water binder ratio is key. So often we find that the water binder ratio is less than 0.3 to achieve this high strength concrete, which is above, say, 60 MPa. So we have to ensure that there's proper selection of binder, and often we find that researchers are using supplementary cementitious material uh, for achieving lightweight, high strength concrete. So when we are using lower water binder ratios, obviously we have to use high range water reducing admixtures. So so I've simplified here a basic proportion of high range water reducer for specified water binder ratios. How am I with time? Gonzalo, am I okay with time, or do you want me
Yeah.
to speed up?
Yeah, I think that maybe five minutes, a little bit more would be fine.
Okay, all right. Thank you. Um, So these are all summary of different types of lightweight aggregate used in lightweight high strength concrete. Like I said, that's the reference that I've used. That's my paper, and you can check the different properties of this type of aggregate. And very often, high strength concrete with lightweight aggregates use fibers. So concrete by itself, it's already weak in its tensile properties. So it's essential to use different, and especially when it's lightweight aggregate, then we have to consider utilization of fibers. So lightweight, high strength concrete, there's various application. And I think Zurich is currently leading the work on curved type of concrete roof using lightweight, high strength concrete. And this is another project from Leica, and it's lightweight aggregate used in Trisford Bridge in Norway. So I'll quickly go through what I'm currently working on in Northumbria University. So we are working on ultra high performance, lightweight, high strength concrete. So we're trying to achieve above 100 MPa. So we are using sintered fly ash, which is LITEC. And like I said, the modified Anderson method is what I use for the mix design purposes. And I'm also, in order to achieve a more sustainable mix, we are leading the work on polypropylene powder type of aggregate in lightweight high strength concrete. So what we are doing currently in Northumbria is we are altering the properties of uh, PP powder. So as you know, polypropylene powders are hydrophobic in nature. They don't mix very well with water or in cement mix. So we are altering and modifying the properties to create a hydrophilic nature so that it will integrate better with the mixes. So these are all some of the mix design and achieve strength, 28-day strength. So you can see we have achieved some above 100 MPa, 120, 100. So this is possible to achieve lightweight, high strength, high performance concrete, above 100 MPa. And one of the things that I want to highlight is we did not use any of the normal silica fume additives. We use everything locally for the local construction companies. Um, that's all the mixed designs. Um, so just to summarize, hardened properties, weakest phase of lightweight high strength we observe is the porous aggregate, not the interfacial transition zone of the cement base. And the weaker the aggregate, the lower the compressive strength, obviously. And lightweight high strength produced from crushed shale seem to exhibit better compressive strength. So for different researchers, they have generally said tried different examples for lightweight high strength concrete. And like what I said, what we use was LITEC and locally available silica to achieve lightweight high strength concrete. So there are challenges for lightweight high strength concrete. So there's still very limited studies or limited guidelines for high strength concrete using lightweight aggregate. And I hope with sharing this presentation, there'll be more people working on this and probably have better, more greener construction material using lightweight aggregate. And just to quickly share, so that mix that I've just shared is a lightweight high performance mix that achieve 120 MPa. So it is possible also to achieve lightweight high strength that has self compacting ability because we are using the high range water reducer. So we have to adjust the mix accordingly to and it's possible to achieve lightweight, high strength, and self compacting abilities. I think that's it from me, Gonzalo. Thank you, and I'm open for questions.
Well, thank you very much, Brabha, for this very interesting presentation. Actually, it is clear that it is a field that it is not. I mean, at least I didn't know much about these aggregates and this lightweight concrete. So, are there questions from the audience? Actually, in the meantime, I would like to, I mean, I was interested also in the deformability, in the ductility of the material, because at some point you were saying that elastic modulus is lower than normal concrete. I guess that this is very much dependent on the density of the aggregates. But
Yes.
I mean, what about the ultimate strain or the strain that you can reach at maximum load? Is it very large as compared with with normal concrete?
It's very similar. Actually, I had a slide, but I removed it at the last minute. It's very similar, Gonzalo, the stress strain curve for the mix. So again, it depends on the compressive strength of the mix design that we have achieved.
And another question: does it have any sense to have fiber reinforced lightweight concrete, or I mean, with some type of fibers, like especially fibers that are not metallic, that are also light?
Yes,
There are-
definitely. Especially with PP fibers, I think if you if the point is to achieve a lighter weight, then probably PP fibers will work. And what we are using here we are using a textile mesh for the lightweight high performance concrete.
Uh-huh. Yeah, that's true. That's true. Okay, thank you very much. So I think there is a question by sorry, Professor Kawashima.
Hi, thank you. I really enjoyed that talk, especially the overview of all the lightweight aggregates. And my question might be naive, but some of the aggregates that you mentioned are volcanic.